We're going to wrap up our lesson 5.5, which of course is wrapping up chapter 5. We've been talking about area, and yesterday we discovered that you can do some estimating with trapezoids, a little bit or a lot better than estimating with rectangles, but you're still dividing up your shape into different intervals. And again, we can use trapezoids. Well, a mathematician by the name of Simpson, I didn't know him personally, but he kind of dabbled with the trapezoid rule and came up with, well, Simpson's rule, which is, again, it's kind of a spin-off of the trapezoid rule. You're going to find out, though, that we don't draw anything. We actually don't have a geometric shape, but we still end up kind of partitioning your region. So Simpson's area, S sub area for Simpson's area, well, his formula takes the height. And now again, it's not really a trapezoid, but it's like the space between them. We actually again call that the height. But he divides it by 3. And then he's going to multiply that by these y values, like the trapezoid rule, except he's going to kind of steal 4 from the next y value, but then just 2 from the next y value, and then that 4-2-4 pattern is going to continue. Again, 4-2-4 pattern is going to continue until you get to the third to last y value. We'll just call that y sub 4. So you get like 2 y sub 4s, and then you'll get 4 y sub 5s until you get to the last y value, which we'll just call y sub n. You just use one of those. So what is this? Well, it's, again, a pattern where you use the first and use the last y value. As I hope you notice, you use them once. And you then, the y values in the middle, we go back and forth with this 4-2-4 pattern, ending with 2, 4, and then again your y value. So it's just a little pattern. Probably the most common question is, one of the observations is that this only works for an even number of subintervals. So again, n has to be even, and again, n is the number of subintervals. And then students will often ask about the height. Remember, the height is just taking your entire interval, the distance of your interval, that is b minus a, and then just dividing it by n, dividing it by the number of subintervals. So we just can end up with our even or evenly spaced apart h values. Simpson's rule. It's on page 292. You don't have to memorize it, but you do have to be able to use it. And let's use Simpson's rule to evaluate an integral. Now, you want to be careful here that you understand my notation. Yes, I'm writing an integral from 3 to 5 of 2x cubed dx. And we're going to let n equal 4. Now, make sure that you understand the notation. I did put an integral on the board, but we're not going to do the integral using the antiderivative. Instead, we're going to do the integral by using Simpson's rule. So when we see this integral symbol, it really just means find the area. But again, we're going to find that area using Simpson's rule. Now, Simpson's rule requires y values. Where do we get y values? How can we kind of organize y values? Well, how about from a table of values? I find the most complicated thing with this is kids just realizing, oh yeah, I need y values that go with some x values. And of course, my x values are going to go from 3 to 5. And this gives us a chance to kind of ponder what other x numbers are going to go in here. Well, that's where h comes in. H, it's the length of each interval. It's taking the space between the interval, 5 to 3, and dividing it equally by 4. So, of course, I get 2 over 4, which is really the same as a half. You see, each of my x values over here is going by an increment of a half. And of course, I didn't really know that until I found the h value. Well, now I just need to plug in 3 and 3.5 and 4 and 4.5 and 5. I'm not going to do every one of these, but make sure that you are processing that we're just plugging into the original equation. We're plugging into the original equation. We're getting a y value. And of course, we need each of these y values. Okay, I'm going to just plug in the first and last one because they're a little bit easier to see. This one's going to be twice of 125, so we call that 250. And you just would go through and compute, evaluate, get each of these y values. I'm going to fill in the rest of them here. Now, we're not making a sketch. But we're still going to use these y values in Simpson's rule. And of course, Simpson's rule says that, forgive me, before we get to the y values, there's the front h over 3, right? H over 3. H is a half. So make sure that it's a half over 3 as your ultimate coefficient. Now I'll take my first y value, which was 54 up here, 54. I'll take 4 of my next y value, so 4 of these 85s, 85, 75, 2 of my 128s, 4 of my 182s, and finally the last y value. Yeah, it worked, didn't it? Were you afraid that it wasn't going to work? Like, were we going to end up with the right pattern? It's going to work because n was even, so the pattern is always 4, 2, 4, and then again I end with my last y value. So I'm going to get 1/6 of the sum of all these numbers. Make sure you can compute that. I'm sure you can. 1/6 of 1632 is 272. 272. Kind of a interesting number. Yeah, it's the highway that connects Lancaster City with the Buck. But it's also, interestingly, it's also related to the actual integral. Now, if it doesn't say use Simpson's rule, if it just says do the integral from 3 to 5, then yes, I would expect that you're using the antiderivative. I would expect that you're finding capital F of x. Make sure you add to the exponent and divide by the new exponent. You get 1/2 x to the 4th. I'm going to leave out the plus c because we know that eventually we're going to be subtracting these numbers. So we got to do some more plugging in. Yeah, you got to do some more plugging in. You end up with 312.5. Having trouble reading my handwriting here. And we end up with 40.5. And when you subtract those two numbers, 312 and 40, you get 272. I'll be. So what's going on here? Is Simpson's rule really that good? Well, it is really that good for a cubic. For a cubic, Simpson's rule is perfect. And so that's a little bit of why we throw this into a calculus lesson. It's a little bit why this mathematician messed around with the trapezoid rule. He was trying to make it better. It turns out that he did make it better, but for cubics, really it's perfect. All right, now there'll be a problem for you to use. There'll be a problem where you want to use Simpson's rule in the assignment. Like I said, you don't have to memorize Simpson's rule, meaning that it's not going to be on the test. Well, speaking of assignments, I wanted to use this video, just the last part of this video, to talk about a mini project that's going to be part of your last assignment. Your last assignment includes book problems and this little trapezoidal mini project. Now, most of this is self-explanatory. I don't want to read things that you can already read, but I do want to just do a little bit of explaining verbally. Sometimes it helps kids to say, okay, yeah, I can do this. Basically, you're going to find the area of a car window using the trapezoid rule. And in order to do this, you're going to need a photograph of a car window. I ask you and encourage you to actually take a photograph, not just steal a photograph off of Google. One of the reasons I want you to take that photograph is because you're going to need to be able to measure one of the sides. You're going to want to measure one of the sides that is like a straight line, but then you're going to be working with the side that is not a straight line. You're going to be using, again, the trapezoid rule to kind of work with that. So a side window, typically like a passenger side window, maybe a driver's side window, work pretty nicely. So you're going to get a picture of a window. Okay, it's something you want to do. If you haven't done it already, you want to have that ready for tomorrow. And then you're going to use Desmos to basically import the picture and stretch it or scale it to actual dimensions. Again, you will have to have measured part of the window so you know what the actual dimension is. Now, once you open up desmos.com/calculator, you're going to want to log in. That way, you'll be able to save your project. You'll be able to save it actually as a unique URL. So when I start doing the project, really, I can change the title up here if I want, but the first thing that you're going to need to do is you're going to need to insert an image. So I go up here to the insert button, the left-hand side, and of course the image, the picture that I took, should be on my hard drive. You need to get it on your hard drive. It actually will paste it in there. Now, basically the reason I'm showing you this is because I want you to understand how the Desmos kind of X and Y axis works. It's a little bit archaic. You have to grab at the middle to be able to drag your image. Next, I'm going to want to rotate my image, that is the angle of the image, so that the graph, so that the horizontal axis of the graph is parallel with the x-axis. So it just kind of makes sense that your image is kind of tilted the right way. It's in radians, so I don't need a whole lot of radians to be able to get it tilted correctly. Did you measure some of your window? Yes, you were supposed to have measured a side of your window. Most people will measure the bottom because it's going to be linear. I measured mine to be 38. So what I'm doing now is I'm dragging the bottom of the window. I'm enlarging the entire window so that the bottom of the window can be drug as far out as 38. A little bit of guess and check here. Right now, the bottom of my window is at about 29. So I need to keep enlarging. I only measured this distance. That is the distance from the left corner to this spot here. It looks like it's pretty close to 38. I'm going to say that it's good enough. So I got my graph kind of scaled and sized correctly so that I can start to find some points. You're going to insert a table. Now, here's usually the most common question with these problems. What numbers go in my table? Well, I'm starting at x equals 0, but because I'm going to have 6 subintervals, since I'm going to have 6 subintervals, remember you have to have at least 6, then I'm going to divide 0 to 38 by 6. Of course, when you divide that, it doesn't come out perfectly. It's 6 1/3. For my problem, it's 6 1/3. And oh, look what Desmos does. It actually automatically gives me the next x value. It's 12 2/3. If I hit enter again, I get the next 6 1/3. Now, I need to make sure I know what's going on here, because isn't my last x value supposed to be at 38? That's because I measured my window already. Well, 114 over 3 is 38. So, oops, I typed over top of it and it just kind of inserted. So I just delete that. Now, the whole reason we're using Desmos is so you guys can find some points. So, where's the points up here along the top? Where's the Y values, I should say? Kind of just have to look at the graph. I mean, I feel like my first Y value at like 6 1/3 is somewhere around 22. I can do better than that. I can do like 22.3, 22.4. That's a good looking Y value. So, are you ready to finish the project? You're going to complete your table so that you have these Y values that you can put into the trapezoid rule. By the way, you could type the trapezoid rule in this space. You could just kind of type it. It's the computer's going to get confused, but you're just using this spot to type out your math. Or you could do it on paper and take a picture of that and attach it to your email. Oh, look, I can now save my project. Now I can actually save it because I started doing something. So trapezoid rule, something to the effect. But if you look up here, now I have a unique URL. So that URL I'm going to eventually copy and paste in an email and send that off to Mr. Naylor, of course, after I finish the project. Don't forget about the bonus. That's kind of neat. It's not actually super hard. It's just more thinking, how else could you do the problem? So that'll be fun too.